Welcome back to Blueprint to Reality. Today, we're diving into a critical topic for modern infrastructure: how engineers make bridges earthquake-resistant. Bridges are vital lifelines, connecting communities and supporting transportation networks. But when earthquakes strike, the forces can be immense, threatening their stability. So how do engineers design bridges to withstand seismic activity? Let's explore the key techniques that keep these structures standing tall during earthquakes. Understanding seismic forces. First, let's quickly understand what happens during an earthquake. Earthquakes generate lateral forces, side-to-side movements, that can shake a structure violently. Bridges are particularly vulnerable because they span long distances and need to support heavy loads, like vehicles and trains. During an earthquake, the ground beneath a bridge can move unpredictably, creating forces that can cause columns to crack, joints to fail, or even lead to complete collapse if not designed properly. Flexibility through base isolation. One of the most effective techniques engineers use to protect bridges is base isolation. This involves placing flexible bearings or isolators between the bridge structure and its foundation. These isolators act like shock absorbers, allowing the bridge to move independently of the ground during an earthquake. By isolating the movement, the bridge can sway with the seismic waves without absorbing the full force of the ground shaking, greatly reducing the risk of damage. Dampers to reduce vibrations. Another key tool in earthquake-resistant design is the use of dampers. Think of dampers as a way to slow down the vibrations caused by seismic forces. Engineers often install tuned mass dampers or viscous dampers within bridge structures to absorb and dissipate energy. These devices can reduce the amplitude of vibrations, minimizing the impact on the bridge's key components like its deck and supports. Dampers essentially help calm the shaking, protecting the bridge from excessive stress. Reinforced pillars and foundations. The next critical aspect of earthquake-resistant design is reinforced pillars and foundations. Engineers use reinforced concrete and steel to strengthen the columns and piers that support bridges. This reinforcement helps resist the intense shear and bending forces caused by earthquakes. In some cases, engineers also use deep foundations or piles that extend far below the surface to reach stable soil or bedrock, ensuring the bridge remains stable even when the ground above it shakes. Expansion joints. Lastly, bridges are equipped with expansion joints. These are gaps or flexible connections that allow different parts of the bridge to move independently during seismic activity. By providing space for controlled movement, expansion joints prevent parts of the bridge from colliding with each other or cracking under stress. They help ensure the bridge can flex without breaking. By using base isolators, dampers, reinforced pillars, deep foundations, and expansion joints, engineers create bridges that can resist the devastating effects of earthquakes. The goal isn't to make bridges completely unmovable. It's to allow them to flex and absorb seismic forces without collapsing. Thanks for watching Blueprint to Reality. If you enjoyed this breakdown of earthquake-resistant bridges, be sure to like, subscribe, and hit the notification bell for more insights into the world of civil engineering and design. Stay safe, and see you in the next video. Welcome to Blueprint to Reality. Today we're talking about some of the most infamous cases of engineering gone wrong. From bridges to skyscrapers, engineering failures can have catastrophic consequences. We'll explore 7 famous structural disasters where mistakes in design, construction, or maintenance led to tragedy. These incidents remind us why precision, attention to detail, and adherence to safety standards are crucial in the world of civil engineering. 1. Tacoma Narrows Bridge, USA, 1940. Let's start with the infamous Tacoma Narrows Bridge, nicknamed Galloping Gertie. Built in Washington state, this suspension bridge dramatically collapsed just months after it opened in 1940. Wind-induced vibrations caused the bridge to sway uncontrollably, as captured in now-famous footage. The design overlooked the effects of wind on such a flexible structure. This disaster revolutionized how engineers approach aerodynamics in bridge design, highlighting the importance of accounting for natural forces. 2. Hyatt Regency Walkway Collapse, USA, 1981. Next is the Hyatt Regency Walkway collapse in Kansas City, Missouri, in 1981. During a hotel event, 2 suspended walkways gave way, falling onto a crowded lobby below. This collapse killed 114 people and remains one of the deadliest structural failures in U.S. history. The cause? A change in the original design for the walkway's support rods, which couldn't bear the load. This disaster emphasized the dangers of modifying structural designs without thorough re-evaluation. 3. Ronan Point Tower, UK, 1968. The collapse of Ronan Point, a residential tower in London, occurred just 2 months after it was completed. In 1968, a gas explosion on the 18th floor caused one corner of the building to collapse like a stack of dominoes. The failure exposed the fragility of precast concrete panel construction and poor connections between structural components. This disaster led to stricter regulations on high-rise buildings in the UK and better safety standards for gas installations. 4. Sampong Department Store, South Korea, 1995. In 1995, the Sampong Department Store in Seoul collapsed without warning, killing over 500 people. The building's failure was caused by illegal modifications to the original structure, including the removal of support columns and overloading of the rooftop. The disaster was a wake-up call about the dangers of ignoring engineering principles in favor of profit, stressing the importance of strict adherence to structural integrity. 5. Florida International University Bridge Collapse, USA, 2018. In 2018, the pedestrian bridge at Florida International University collapsed just days after its main span was installed, killing 6 people. The collapse occurred due to design flaws in the bridge's tensioning system, which created cracks that went unaddressed. This tragic failure underscored the importance of early detection of structural problems and following protocols during construction. 6. Rana Plaza Factory Collapse, Bangladesh, 2013. The Rana Plaza factory collapse in Bangladesh is one of the deadliest structural failures in history, killing over 1,100 workers in 2013. The building, which housed multiple garment factories, was poorly constructed with substandard materials and unauthorized floors. The collapse revealed the extreme dangers of cutting costs at the expense of safety and led to worldwide scrutiny of building regulations in developing countries. 7. Savar Building Collapse, India, 2017. The Savar Building collapse in India, also known as the Lotus Business Park fire, involved the collapse of an under-construction building due to poor materials and design. This incident highlighted the need for quality control and proper oversight, particularly in fast-growing urban areas where construction standards may be compromised. Each of these disasters demonstrates what can happen when engineering goes wrong, whether through design flaws, cost-cutting, or poor execution. But they've also paved the way for better practices, stricter regulations, and new technologies. Thanks for watching Blueprint to Reality. Be sure to like, subscribe, and hit the notification bell for more content on engineering, design, and the lessons we can learn from past failures. Stay safe, and we'll see you in the next video. Welcome to Blueprint to Reality. Today, we're diving into one of the most impressive feats of engineering, suspension bridges. These towering structures seem to defy gravity, effortlessly hanging between 2 points. But what's the secret behind their strength? The basics of suspension bridges. At first glance, suspension bridges are marvels of simplicity, but don't be fooled. The science keeping them standing is anything but basic. A suspension bridge consists of 3 key parts: the deck, cables, and towers. The deck is the part of the bridge you drive or walk on, but it's not just resting on solid ground. Instead, it's suspended by cables, massive steel ropes that connect the deck to the towering vertical structures on either end, called the towers. These towers hold most of the weight. How suspension works. Now, here's where the physics comes in. Those steel cables are the backbone of the suspension system. When a load like cars, trucks, or even people moves across the bridge, it creates downward force on the deck. The cables take that force and spread it across the entire span of the bridge. They transfer the load to the towers, which then transfer it down into the ground, or foundations, deep beneath the surface. Think of the bridge as a giant hammock. The cables are like the ropes of the hammock, and the deck is like the fabric. The weight on the bridge causes tension in the cables, but the towers act as anchors, keeping everything in balance. Stability and flexibility. An important feature of suspension bridges is that they're designed to be both strong and flexible. In fact, flexibility is crucial. Winds, temperature changes, and even earthquakes can cause the bridge to move slightly. That movement helps it absorb stress instead of breaking. Engineers calculate how much sway a bridge can handle to ensure it stays standing, even in harsh conditions. The cables are made from thousands of smaller steel wires twisted together, allowing them to carry incredible weight and remain flexible enough to handle shifting forces. So the next time you drive over a suspension bridge, take a moment to appreciate the science at work. It's not just concrete and steel, it's an intricate dance of tension, weight distribution, and flexibility. That's the magic that keeps these bridges standing tall and strong. Thanks for tuning in to Blueprint to Reality, and we'll see you next time.